Swayam Prabha. Digital India. Educated India.
Continue our discussion on invertible matrix. You remember last time we started the discussion on invertible matrices, and we gave some equivalent criteria for when a matrix is invertible. And we proved that invertible matrices are those which are product of elementary matrices. All elementary matrices are invertible. Those are matrices corresponding to the three elementary row operations. Those matrices are invertible, and we proved that any invertible matrix is product of elementary matrices and vice versa. So in that sense, elementary matrices are the building blocks of all invertible matrices. Okay. We also proved a equational criterion for invertible matrices. We showed that a square matrix A is invertible if and only if look at the homogeneous system of linear equations, then this has only solution, only the zero solution if and only if A is invertible. And we also proved that if A times B equal to identity, then A is invertible. And B is the inverse of A. Okay, so we only need to check one condition, that A times B is identity, and the other condition B times A is equal to identity will be automatically satisfied. And we also looked at the row canonical form, that A is invertible. A is invertible if and only if the row canonical form of A is the identity matrix. Okay. So let us continue further discussion on invertible matrices. Right. So suppose we have a square matrix of size n by n, and there is a B, so that either BA is identity or AB is identity. Then A is invertible and A inverse is B. If A times B is invertible, then both A and B are invertible. Okay. So if B times A is identity, then I multiply this by the column vector x, and I get BAX is equal to x, because BA is identity. So if AX equal to 0, okay, if AX equal to 0, then by this equation, yeah, BAX is also 0, but BAX is x, and therefore x is equal to 0. So by the equational criterion for square matrices, a square matrix is invertible if and only if the homogeneous system AX equal to 0 has only trivial solution. Okay. So A is once BA is identity, then we have proved that A is invertible. And suppose C is its inverse. Suppose C is inverse. Then BA is identity. So C is equal to BA times C, and that is equal to B times AC. And C is the inverse of A. So AC is identity, and therefore BAC is equal to B. And therefore the inverse of A is actually this matrix B. Okay. So hence B is the inverse. And by similar technique, we can prove the other criteria. If AB is invertible and its inverse is D, if AB is invertible and suppose the inverse is D, then AB times D is equal to A times BD, and that is identity. And so A times BD is identity, so BD is the inverse of A. Okay. So if AB is invertible, then A is invertible. Similarly, we can prove that B is also invertible. Okay. So factors of an invertible matrix are invertible, and product of invertible matrices is also invertible. This we have proved before, because we proved that inverse of A times B is B inverse times A inverse. Okay. So suppose we have a square matrix which is invertible, and we want to solve a system of linear equations which is inhomogeneous, Ax equal to B. Okay. So if Ax equal to 0 and A inverse exists, that means x is equal to 0, because A inverse A x equal to Ix, and that is equal to x. Okay. So the homogeneous system for invertible matrix has only the 0 solution. So we look at the inhomogeneous system, Ax equal to B, where B is given. Now, in order to solve this system of linear equations, we look at the augmented matrix as we did before, AB, and then we know that the row canonical form of a invertible matrix is identity matrix. So by applying elementary row operations, this augmented matrix AB can be converted into IC, right? So by a sequence of elementary row operations, we convert A into I, and those elementary row operations will convert the vector B into C. Okay. So therefore, Ax equal to B if and only if Ix equal to C, because the system of linear equations which is given by this augmented matrix IC has same solution as the original system of linear equations. Applying elementary row operations does not change the set of solutions, but it changes the set of linear equations. So Ax equal to B if and only if X equal to C for X in R, X a column vector, and therefore X equal to C, right? Ix is X, so X equal to C, and therefore I substitute into X equal to B, and I get AC equal to B. Okay. So that gives a algorithm to find out solution of inhomogeneous equation using Gauss elimination method. Okay, you can say that this why we need to do this, because if A is invertible, then we look at Ax equal to B multiply by A inverse, and that gives me Ix equal to A inverse B, and therefore X equal to A inverse B, right? X equal to A inverse B, but the problem is we have not found A inverse. Okay. And this Gauss elimination method, we will see later, it will calculate A inverse, but it also calculates the solutions. So we look at the augmented matrix AB by elementary row operations, convert A into identity matrix. Those elementary row operations will convert B into C, and then this C is the solution. Okay, because Ix equal to C, if you write down the system of equations corresponding to Ix equal to C, it is just saying that x1 equal to c1, x2 equal to c2, and xn equal to cn, and therefore x equal to c, right? So therefore c becomes the solution of the inhomogeneous system of linear equations. Okay, and it is a unique solution, right? So this observation is the basis of important method to find the inverse of a square matrix, and this is called the Gauss-Jordan method of inverse of a matrix. You might have learned in school that inverse of a matrix can be found by using cofactors and determinants, etc., etc. That those formulas are useful to some extent. They are computationally very heavy. I will discuss those formulas also. But an efficient method to calculate inverse of a matrix is the Gauss-Jordan method, which is dependent on what we just observed. That if we have invertible matrix Ax equal to B, then a solution can be found by converting A into row canonical form, and those elementary row operations will convert the vector B into a vector C, and that C is the solution. So let us use this fact to understand the Gauss-Jordan method to find inverse. So let's consider an invertible matrix. Yeah. And suppose C1, Cn are unique elements, so that AC1 is E1. Yeah. So we just proved that if I look at the equation AX equal to E1, then there exists a unique C1 such that AC1 equal to E1. Okay. So similarly, we find unique C2 so that AC2 is equal to E2, and unique Cn so that ACn is En. Yeah, we solve this n system of linear equations, inhomogeneous linear equations. Okay, by converting A into the row canonical form. Okay, we can do this solving these n equations in n unknowns, n systems of n equations in n unknowns simultaneously by constructing a matrix C. Yeah. So we want to find this matrix C whose column vectors are C1 to Cn, so that AC1 is E1, ACn is En. But you see, A times C is can be multiplied like this. Display the column vectors of C, then the column vectors of AC are AC1, AC2, and ACn, right? But AC1 is E1, AC2 is E2, and ACn is En. So A times C is this matrix, which is identity matrix, and therefore C is the inverse. Yeah. So once I get AC equal to identity, then C is inverse. So what are we doing? We are simultaneously solving these n system of linear equations in n unknowns, and the right hand vectors are E1, E2, En, and this we do simultaneously. So this, by last corollary, it follows that this matrix C that we find by solving these systems of equations is the inverse of A. Okay, so to find A inverse, we solve these system of equations: AX1 equal to E1, AX2 equal to E2, AXn equal to En, and we can do this simultaneously by making a big augmented matrix. Yeah. So if we have one system of linear equations, I just add the vector B and make an augmented matrix. But now we are solving n systems of linear equations. So I make this E1, E2, En, and this bigger augmented matrix, which has n rows and 2n columns. And this we write notation AI. I is the identity matrix. Okay, and now we transform. So this n by 2n matrix is there. We apply row operations, elementary row operations, to convert this n by 2n matrix into row canonical form. And since A is invertible, the row canonical form of A will be identity. Okay, so AI is transformed into identity, and then this matrix, identity matrix, is transformed into C. Okay, and this C is the inverse. Right. So it is saying that if I want to find inverse of a matrix, then just put identity matrix and make this n by n by n by 2n matrix, and do elementary row operations until we reach identity matrix here. Then this matrix get transformed into A inverse. So this is the algorithm to find Gauss-Jordan algorithm to find inverse of a matrix. Okay. So to carry out the above process, we need not know beforehand that the matrix is invertible. So we showed last time that if I am given a n by n matrix, to test whether it is invertible, we just try to find its row canonical form. And we proved that the matrix is invertible if and only if the row canonical form is identity matrix. So we just set up the equations AX1 equal to E1, AX2 equal to E2, etc., and apply Gauss-Jordan process. At the end, suppose the row canonical form of A doesn't turn out to be identity matrix, then it says that the matrix is not invertible. Okay, say the matrix is not invertible, and therefore in this case AX equal to 0 will have infinitely many solutions. Okay, so so this process itself reveals that whether A is invertible or not. So let's look at an example. look at this 3 by 3 matrix. Okay, look at this 3 by 3 matrix. It's not clear whether this is invertible or not right now. Okay, so this is a coefficient matrix of a system of linear equations in 3 unknowns, and there are 3 equations. Okay, so use elementary row operations to transform the augmented matrix. This is a 3 by 6 matrix. Yeah, they convert this into. We will try to convert this into row canonical form, which may or may not be identity, and then this identity matrix is transformed into the matrix C, and that is likely to be the inverse if A is invertible. Okay, so we have gone through this process. Convert this. This is the identity. We juxtapose identity matrix with the original matrix, and then try to convert this 3 by 6 matrix into a row canonical form. And we find that this is the row echelon form. Yeah, this is row echelon form. But now we have to go into Gauss-Jordan method, and starting from -5, we have to convert these into zeros. Then we convert this into 0. But before that, these pivots, these 3 pivots, have to be converted into ones. So at this point, it is clear that the original matrix is invertible. Yeah, the original matrix is invertible, because what has happened is original matrix was A, and then we applied some elementary row operations E1, E2, ER, and then this becomes this matrix U. Okay, this matrix U is upper triangular matrix, and the diagonal entries are non-zero. And we showed that if I have a system of linear equations whose coefficient matrix is upper triangular and diagonal entries are non-zero, it has a unique solution. Okay, it has unique solution. So therefore this matrix A must be invertible. And now we convert this into the row canonical form, yeah, by elementary row operations, and this is what we end up with. So the original identity matrix, this identity matrix by these elementary row operations is converted into this. This matrix A is converted into identity matrix. So A is invertible, and this is the inverse. This is the A inverse. Okay, and we can simplify convert the decimals into fractions, and A inverse is 1/10 and times this 3 by 3 matrix. It is one of the most efficient methods to find inverse of a matrix, or solve a system of inhomogeneous equations Ax equal to B where the matrix is invertible. The chapter on determinants will be discussing basics of theory of determinants. Our aim is not to calculate determinants of complicated looking matrices, but we want to understand how determinants are defined, what are the fundamental rules about determinants of matrices. Okay, so you have studied in school determinant of product of two matrices, product of determinants, and then using determinants you also know the formula for inverse of a matrix, yeah? And then Kramer's rule, and determinants. Determinant of transpose of a matrix is equal to determinant of the original matrix, and so on. So these are some basic facts, and we want to prove these basic facts or determinants without really using a formula for determinants. Okay, the formula will come out as a consequence of our discussion. Okay. Determinants of, you have seen determinant of 2 by 2 matrices, 3 by 3 matrices, and those are complicated looking formulas. You were just told this is the formula for determinant, but where it came from? What is the genesis of determinant of a square matrix? So determinants are associated with square matrices. If I have a n by n matrix, then its determinant will have n factorial terms. It's a very complicated function. Yeah? If the determinant, if we are computing determinant of a real square matrix, then determinant is a real number, and it's a function of n square entries of the matrix, and the formula has n factorial terms. It's a very complicated formula, and you might have wondered, no, why somebody came out with such a complicated formula and why it is so useful. Okay, So we will clear all these mysteries by treating determinants in a axiomatic fashion. You know properties of determinants. So those properties are, one of the properties that determinant of identity matrix is 1. It may look a trivial fact, but this becomes one of the defining properties of determinants. Similarly, if I take a matrix where two column vectors are identical, its determinant is 0. Or whether if two row vectors are identical, determinant is 0. And determinant is a multilinear function. It is linear in every column vector or every row vector. Okay, so we will take these 3 properties of determinants, which you know, as our characterization of determinant function. Okay, so let's approach in a axiomatic manner the theory of determinants. I'm sure you will enjoy this new way of approaching determinants. So let's begin. We set up axioms of determinant-like functions. Okay, and then we will prove the existence and uniqueness of this. We will prove determinant of product of 2 matrices is product of the determinants. Then invertibility of a matrix in terms of determinant. We will show that determinant is non-zero if and only if the matrix is invertible. Then we will compute determinant by Gauss-Jordan method. We used Gauss-Jordan method to find inverse of a matrix, but the same Gauss-Jordan method can be used to compute determinant. When I say Gauss-Jordan, we really mean the given matrix is being converted into row canonical form. Okay. If we do not insist on row canonical form, you just want to find the row echelon form, then it is called Gauss elimination method. Okay, but if you further continue and convert the matrix into row canonical form, then that method is usually called Gauss-Jordan method. We will find inverse of a matrix in terms of the cofactor matrix. Then we will approach Cramer's rule, which you know for 2 by 2 and 3 by 3 matrices for solving n linear equations in n unknowns. This is not an efficient method, but the formula is attractive, and you know this formula for 2 equations in 2 unknowns and 3 equations in 3 unknowns, but it is valid for n equations in n unknowns. And we will write down the formula for solutions of a system of linear equations where the coefficient matrix is invertible. That is called the Cramer's rule. Okay, so let's proceed to the axiomatic approach for determinant function. Yeah, so determinant of a 1 by 1 matrix consisting of 1 entry is A. Okay? And by convention, if a matrix has 0 rows and 0 columns, that means there is no entry, then by convention its determinant is supposed to be 1. Okay, it's just by convention. Determinant of a 2 by 2 matrix whose row vectors are AB and CD is AD minus BC, and then determinant of this 3 by 3 matrix has these 6 terms, right? So it becomes more and more complicated as the size of the matrix increases. Okay, so we want to approach the theory via their properties. Okay, so we will say that a function is a determinant function if it is acting on n by n matrices where the entries are taken from some number system. The number system could be the system of real numbers or complex numbers or rational numbers. So f will denote a given set of scalars. Okay, it could be real or complex or rationals or some other field. Okay, so fix the set of scalars as f. Okay, f is for field. Then every n by n matrix where the entries are in this field of scalars, this function will be called determinant function if it satisfies certain properties. So suppose the column vectors of the matrix are a1, a2, an. We will think of determinant function or determinant-like function as a function on the column vectors of the matrix. Okay. So we have space of all n by n matrices. So n is fixed, and then we are thinking of the determinant function as a function of the column vectors. So write the column vectors a1, a2, an, we'll define this function dA to be d of a1, a2, an. So there are there are n arguments in this function, and those arguments are ordered sequence of column vectors of the given matrix A. Okay. So this function is acting on the space of n by n matrices, and the output is a scalar in the field F. This is called a multilinear function. It's called a multilinear function if so if every k and all scalars alpha beta, right, and these column vectors of the matrix and B and C are other column vectors. Look at the matrix whose column vectors are A1, AK minus 1. These are the first K minus 1 column vectors of the matrix. But the kth column vector is this linear combination of B and C. Okay, alpha B plus beta C. So B and C are column vectors with n components. And I take this linear combination of B and C. And the kth column vector of the matrix now is alpha B plus beta C. And then I keep the other column vectors, say K plus 1 AN. The multilinearity means that I am fixing the other columns and I'm changing the kth column. Okay, and I take a linear combination of two column vectors. Then this is linear in this coordinate, kth coordinate. So it is alpha times d a1 ak minus 1 b ak plus 1 n plus beta times d of ak a1 up to ak minus 1 c ak plus 1 an. Okay, so alpha and beta they come out of the this function d. Okay, and we can separate b and c. Okay, so this is called multilinear property because this property is satisfied in for each one of the column vectors. Okay, this is the multilinear property. So d is called multilinear if we have this equation holds. That's the condition for multilinearity. D is called alternating if whenever ai equal to aj, that means the matrix has two equal column vectors, then d of this matrix is 0. Okay, so alternating means two column vectors are equal, then the determinant of this matrix is 0. Yeah, then determinant of identity matrix is 1. So this we say this is the normalization property. Yeah, so it is giving a value to the determinant of identity matrix. Okay, there can be many functions which are multilinear alternating, but they are not normalized. So determinant of identity matrix may not be equal to 1. Yeah, for some multilinear alternating functions, we will come across those things. So focus on these three properties. So this function D is from the space of n by n matrices, and the output is a scalar. If it is multilinear, alternating, and normalized, then we say it is a determinant function of order n. So there can be many functions on the space of matrices. But this function, which is multilinear, alternating, and its value on identity matrix is 1, is called a determinant function of order n. Okay, and we want to show that such functions are there is only one function of this kind. Yeah, there is only one function of this kind, and it exists. So we have to show existence and uniqueness of determinant functions on the space of n by n matrices.